So this means we have the general trends down, so we should be able to look at actual atoms in our periodic table and graph them and see that they match up with our trends. So here we have that graphed here. We have atomic number Z graphed against ionization energy. So let's fill in what the actual atoms are here. And we can see, in general, yes, we're following the trend. For row 1, we're increasing, as we should, across the row. Let's look at row 2 also. Well, we're generally increasing here. We'll talk about that more in a minute. And also in row 3, yeah, we're generally increasing. There's some glitches here, but the general trend holds true. Similarly, we see as we go down the table, so as we're going from one row to the next row, so for example, between helium and lithium, we see a drop. The same with neon to sodium, we see a drop here. So it looks like we're generally following our trend. That's a good thing. But hopefully you will not be satisfied to just make a general statement here when we do have these glitches. So you can see, for example, we have several places where instead of going up as we go across the row, we actually go down in ionization energy a little bit. So between B, E, and B, between N and O, magnesium and aluminum, and then phosphorus and sulfur, what we see here is that we're kind of going down, or quite specifically, we are going down. So let's take a look at one of these rows in more detail to think about why this might be happening. And it turns out the reason that these glitches occur are because of the subshell structure predominates in certain instances, and that's where these glitches take place. So I've sort of just spread out what we have as the second row here, graphed against the ionization energy. So let's consider specifically where these glitches are taking place. So let's look at the first one between beryllium and boron here. And the glitch that doesn't make sense just through periodic trends is that it turns out that the ionization energy of boron is actually less than the ionization energy of beryllium. So I put the electron configurations and actually drew it on an energy diagram here so we can actually think about why this might be happening. So what is this? Which element did I chart here? Which one is that, the boron or the beryllium? I couldn't tell what you said, sorry. So I'm going to assume that was beryllium, and then it turns out that if that's beryllium, the other one must be boron. So we have beryllium in the first case here. It has 4 electrons. That's how we know it's beryllium. Boron has 5 electrons. So just looking at putting in the electrons, filling up the energy diagram here, we should be able to see a little bit why this is happening. And the reason is simply because the energy that we gain in terms of moving up in Z, so from going to Z equals 4 to Z equals 5, is actually outweighed by the energy it takes to go into this new shell, to go into this new subshell. So to jump from the 2s to the 2p takes more energy than we can actually compensate with by increasing the pull from the nucleus. So it turns out that in this case, and any time that we see we're going from a 2s to a 2p, filling in of electrons, we actually see that little bit of a glitch in ionization energy. So it's shown here for the second row, but it's actually also going to be true for the third row. The same thing when you're going from filling in the 2s to putting that first electron into the 2p.